let's get started. I'm sure there's more people that will filter in, but as usual, we have a fair amount of stuff, and I want to be able to talk about it. Today should be fun. We're going to talk about interactive proofs. Who here has heard of an interactive proof in the setting of computer science? Yeah? Sort of heard of it. Would you feel comfortable giving a formal definition of it if I asked you to? Not so much. Okay, cool. That's fine. We don't expect a lot of formal definitions out of IP. IP, we're going to introduce it here, and I'm not going to give the most formal definition because it plays a fundamental role when we get to like zero knowledge proofs and certain things like that. But we don't want to get to like the complexity theory side of things just yet. Because otherwise, I mean, we could spend lectures and a whole course on IPs. But they are very cool. It's actually one of the most interesting innovations we've had in theoretical computer science, TCS, in the last few decades. So this is pretty cool. So as usual, we're going to deal with some decision problem. But unlike usual, so up until now, we've had sort of one body, one entity that is trying to decide this problem. So we have some function from any number of bits to a decision, accept or reject, and it was okay, if you have a single computer, can you do that, can you not, how long is it going to take you, and so on. Now we're going to say, okay, what happens if we have multiple parts? And so, okay, if we have multiple computers working on this, what happens? And what's the obvious thing that can go wrong if we're dealing with multiple parts? Are they all honest? That's what we're going to deal with. And this is, you can sort of see some of the motivation. If we're dealing with multiple parties, what you might want to do is you might want to like delegate. Let's say you want to delegate computing something, you have some very difficult decision problem or some other algorithm, and you want to ask Amazon, go compute this for me in your cloud. Amazon, Google, Meta, whoever. You want to say, go compute this for me. How can you be sure that they actually do it properly? If I'm Amazon, if I, rather than spending all of the compute time to actually come up with the answer, why don't I just flip a coin and give you an answer? It'd be a lot cheaper for me, right? So, yeah, we'll talk about what some of that means. And debating. You know what? I'm going to do a different example first because this really motivates it. I was going to dive into Merlin and Arthur. Just put these aside for a moment and let's talk about who here's a fan of cola? Who here likes Pepsi? Pepsi? Anybody? No? Coke? No? Okay. You can tell this is not North American. Nobody has an opinion on this.
Yeah, isomorphic or hypothesis.
So, let's say you have some friend, Bob, who says, I can tell the difference between Coke and Pepsi. Or maybe like your favorite bubble tea house versus some inferior bubble tea house if you prefer. Whatever you want as the example. And let's say Alice is the person on this side, doesn't really matter. And it's like, I can tell apart Coke and Pepsi. And Alice says, really? Prove it. So the claim is that Bob can do this. That's what we want to prove versus not. What can we do here to prove this? How could Alice and Bob go through it? Alice doesn't think Bob is wrong, but doesn't think he's necessarily right either. How could we design some sort of a protocol to check this? What could Alice do?
A blind taste test.
Blind taste test, exactly. So give it to me a little more step by step. What's Alice going to do?
He's going to randomly flip a coin and randomly pick one of the two drinks.
Yes, so we're going to take, as usual, some B, flip a coin randomly, and then we're going to send Bob some glass, Pepsi. And if B is 0, Coke. Bob tastes it and sends back so B prime. And what's the last step? What does Alice do at this point?
Check if B equals B prime.
Yeah. If B is equal to B prime, you accept, right? That's kind of like the cryptographic games that we've been talking about this whole time. So kind of similar. Okay, so let's talk about a few different cases. First off, if Bob actually can tell about Coke from Pepsi. So if our claim is true, what is the probability that Alice accepts? Yeah. So the probability that Alice accepts, given that Bob, let's say, claims true. It's going to be too long. Claims true is 1. All right. What if Bob is actually lying? Or just, Bob's trying to show off that he doesn't actually know Coke from Pepsi. What's the probability that Alice accepts in this case? Yeah. Bob's going to have to do a random guess. He's going to guess probably half. How much computing does Alice need to do? Like, how much work does she need to do?
Constant.
Pretty much. I mean, it depends on the size of the glass, right? But whatever the cost is to pour this image, it's pretty straightforward. So, fairly efficient. And certainly, like, if we imagine there's some cost to differentiating between Coke and Pepsi, she certainly doesn't have to do that. Bob can do it, and she can verify, can Bob actually do this? I'm going to put a question here. Think about it as we go through more of the definition. Let's see, what happens if you have an unknown glass? This is an extension. I have never, people usually stop here. And it's sort of the point of the exercise. They've just proven this claim that Bob can tell apart Coke and Pepsi. And for me, that's like, that doesn't really get to all of it. What if Alice unknown glass of, I'm going to say soda pop, because this is one of those linguistic regionalities. It's actually, you can see a map if you go online and search for it. Different parts of the US and Canada call it soda and pop. And there's some parts that even call everything Coke. Interesting random linguistic thing. It's okay. Think about that as we go through a little more of the definition. I'm going to introduce these characters, Merlin and Arthur, because as you can tell, the TCS nerds that we are, a lot of things in terms of Arthurian legends, and the idea is that Merlin is some all-powerful wizard, computationally unbounded. Merlin can solve everything. You can give Merlin a TQBF that is as long as you want, and Merlin will solve it. But you're not Merlin. You're Arthur. And Arthur is a mortal. Polytime, I'm going to say polynomial time. Okay? And what they're going to do is we're going to send messages back and forth. I'm hoping I don't have my, I think this is the correct order. I've done this sort of off the top of my head. I may have these alphas and betas backwards compared to some literature. But the idea is that Arthur is going to send some message to Merlin. Merlin's going to send some message in response. They both have X. You know, there's no disagreement on X or what the decision problem is. They both know what F is, they both know what X is. And they're going to exchange these messages. Did I use your M? Yeah. So you have 2 M rounds of communication. And at the end, Arthur is going to accept or reject. That's again our 0 and 1 from the decision problem. And we assume Arthur is, for some definition, honest, because otherwise, you know, Arthur could just reject everything or accept everything. If Arthur's not honest, it's sort of, the whole thing is trivial. But the prover, Merlin, may or may not be honest. So the protocol is going to prescribe what does Arthur do, what are these messages, but the prover can deviate from the protocol. And we're going to talk about that. So, in general, this is the verifier, and this is the prover. We moved away from Merlin and Arthur, but I just introduced the characters as such for the motivation, and because you will see those names show up, and especially the computational complexity class names. You will see Merlin, Arthur, Arthur, Merlin, and so on for different classes, and we'll talk about that a little bit. But just in case you see them later, you'll understand where they come from. Okay. And so the idea is, what we really want is at the end of this, that Arthur will accept if X is an L and reject if not. So, can everybody give me an idea of like what some properties we want to this? And I sort of said informally what this is, but formalize it a little bit. If X is in L, what would we ideally like out of this? So I'll start with, we'll start over here. So if X is in L, then what would we like to have happen here?
Completeness.
Completeness, yeah, that's the name of it. But what is completeness? What does it mean?
Probably that verifier set equal to 1.
Yeah. So
some constant.
yeah, probability that I'll put B accepts, just to get us used to the verifier prover notation. We want this to be greater than something, but we actually don't want it to be 1. If we disallow any wiggle room here, it actually collapses things down. It gives us no room for expanding past basically. But in any case, 2/3. Sort of the standard definition. We will show later, actually I don't know if we'll get to it in this class, this 2/3 is kind of arbitrary. Moreover, if it's anything more than a half, you can actually amplify this. And using standard shifts we've talked about already in this class. So, all right, and similarly, if X is not in L, what do we want?
In that sense, we go to 1/3.
Yeah, something. Probability that the verifier accepts, we want it to be relatively small. And I think we've talked about it a little bit in this class, and we talked about RPP and some of the randomized classes. But basically, any gap beyond a half, you can amplify. Obviously, if both are perfectly a half, then we can't do anything. But if one is like a half plus epsilon here, and this is a half minus epsilon, you can amplify it. It might cost you a lot, but it'll amplify.
So
This is why we use 1/3, 2/3. Because from 1/3, 2/3, you can amplify this using a number of different techniques, and it'll affect your message complexity and so on. But yeah, so let's talk about that. We've sort of defined what we want computationally. What are other costs? So what do we have to make sure of here?
The interaction?
Yeah. How many messages can we send back and forth? So if our messages are like polynomial in n, that's going to start to get costly, or worse, like exponential in n. So for every, not even every bit, for like every possible value of n, we have to send things back and forth. That's going to be very, very costly. What we ideally want is a constant number of rounds. And it can be shown that if you have a constant number of rounds, you can reduce it down to 2. So
you reduce it down to 2?
if I remember, I don't remember if it's 2 or 3.
Oh.
But yeah, you can always, if I remember correctly, there is a theorem that you can take a constant number of rounds, and you can almost collapse it down. There's a bunch of really cool theorems around IP. We don't have time to get to today because just they get really deep. The proofs of them get really complicated, but they're very cool. So for example, with that definition in mind, let's talk about class MA. So, it's in green just because I can. Class MA. Basically, Merlin, gosh, the prover says one message to aka the verifier. So Merlin can spend as much time processing as he wants to. He can do everything. And he's going to send something to Arthur. And Arthur, in polynomial time, is going to make a decision of whether or not X is in L. What does that remind you of? Another very fundamental class of problems.
NP.
Yeah, this is NP. So, where did I write that down? Yeah. So, you can show fairly easily that NP is in.
I want to clarify. So X is knowledge that Merlin claims to know. Is that correct? How do you show it? Where does X and L come in?
So,
That's the
yeah,
problem.
Merlin is going to claim that X is in L,
Oh, okay.
and is trying to convince Arthur of the fact that X is in L. Yeah. An honest prover, if you give an honest prover some X that's not in L, the honest prover should just reject and say, like, no, this is not actually in L. And therefore, just, it's kind of trivial. What we want to say is that for other prover strategies, you cannot convince Arthur of anything unless X is in L. Yeah. Yeah, it's sort of like this Pepsi Coke idea. The claim is that Bob can differentiate Pepsi and Coke. If we take him at his word, say like, yeah, of course, we trust him, he's Bob, whatever, then the whole thing's kind of trivial. You trust him? Yeah, sure, we trust him. We're like, Bob's kind of a funny guy. Maybe he's right, but let's find it, let's check. And so we want to make sure that if the claim that X is in L is not true, we stand a strong probability of rejecting the statement. So that's what we're looking for.
I suspect the suddenness, the error could be largely equal to 1 over 2 to amplify, because you can use an AND gate to amplify.
Yeah, there's a lot of things you can do to amplify. So yes, you can do repeated trials and require that all of them pass. You can do repeated trials and take a majority vote. There's a number of ways you can do it, depending on which protocol you're looking at. The majority vote's the most common,
Okay.
but not the only one. So yeah, I forgot to put my labels here. This is completeness, and this is soundness. And what we also want is some efficiency. And so, obviously, verifier must all the time. And we also have communication complexity. So, yeah, so in the end, we want some bound on communication complexity. And you can have different discussions of, how much communication you have and so on. But that's what we mean by efficiency here. We talked about NP, and it's obvious, you just send the witness. More not traditionally, but more IP-ish is if we have the class Arthur Merlin, which is Arthur sends some value A1, Merlin sends B1, and then it's just the verifier runs on X, alpha, beta, and gives either accept or reject. An important thing with Arthur Merlin is that you'll notice there's no random input here. And that's intentional, that's explicit. Arthur has no private randomness in class AN. In general IP, you can. For example, here, how important is it for Alice to keep secret what the value of B is? If Bob finds out B, what happens?
I would just call you.
Yeah, Bob can just cheat. So, we'll talk about, we may or may not talk about later, but yeah, there is a transform from anything that uses so-called private coins to an interactive protocol that only uses public coins. An interactive protocol uses public coins, in this way it's called AN. Wow. I get shorthand, but I don't think I should be doing that with shorthand. Okay, we talked about Coke versus Pepsi. Okay, I want to give you a more in-depth example using graph non-isomorphism. I'm going to erase this question, come back to it. Who here is familiar with the term graph isomorphism to graph non-isomorphism? What's a graph isomorphism?
A mapping into graphs, the norms of graphs such that the edges are observed and the mapping is projected.
Yes, exactly. So if you have some graph, where's my blue marker? So, graph. G and I. So I'm going to say if you have G is equal to G1, Y1, G2. So they are isomorphic. I'm going to say this in words and not write it down because like writing this down is just going to take a long time, but I think you'll all get it. If there's some permutation of V1, if we imagine V1 is ordered, as like you would normally get like an adjacency matrix or something like that, there's some relabeling or remapping of V1 such that it exactly equals V2 and E1 will equal E2 in that case. So if you relabel the vertices. Yeah, so if, yeah, what the heck? You can use 3 bars. If and only if there exists this V1 is size of V2 is equal to n. Exists some permutation. There we go. So that's in math notation, but you get the idea. The idea is that we can permute the vertex set and get the other. So what the problem is, the statement x is in, so G1, G2 is in G and I. If and only if it does not exist are such that so the two are not isomorphic is the class G and I. Not class, it's problem, the decision problem, or language. So what class of problems is this in? Is this in NP? What's the witness if it's in NP?
A permutation.
Sorry?
A permutation.
But the point is that there is no permutation. This does not exist. There is no permutation such that, or you can say another way, for any permutation, for all permutations, this does not hold.
With Cohen Cleave.
Cohen, exactly. So, G and I is in Co-NP. And the best known algorithm, I'll just say this, is from Babai in 2016, 2 to the log n to the O1. So basically polylog n, 2 to the polylog n is the best known algorithm for this. Okay. Well, can we build an interactive protocol for this? So, is it easier if I write it here, or should I go to the other side of the board? I'll start here, and hopefully it doesn't get too squishy. So let's write an interactive protocol. So we have our prover, we have our verifier. And think in terms of the Pepsi versus Coke example. What could we get Merlin, Bob, whoever over here, Ruth Bader Ginsburg, I was thinking Grace Hopper. Grace Hopper invented compilers. She's a total badass, but in any case. So somebody who's just like wicked good with computer science, and you want them to prove to you that, these do not have an isomorphism. What can we do? Any thoughts? This is a tricky one. This is admittedly somewhat tricky. Let's think in terms of the Pepsi example, Coke versus Pepsi. If we flip a coin here, and we take either G1 or G2, and we just send it to Merlin. And we ask Merlin, is this Pepsi or Coke? Would that work?
But Merlin knows G1 and G2, right? It's part of the problem statement.
Yeah, so it knows G1, G2. But we sort of want something to that same effect.
Could you permute the graph you choose?
Exactly. What we're going to do is we're going to sample some random permutation of the space of all permutations, and we're going to sample a random bit E. And what we're going to do is we're going to send over G prime, which is this random relabeling of G subscript.
We need to assume the existence of pseudo-random permutation to make this work.
No, we can assume we have sufficient randomness.
But the permutation, that part,
Yeah, so this permutation is truly random.
truly random,
Truly random. We don't care about the cost of randomness right now.
can be efficiently sampled.
So remember that the prover is all powerful.
But right now, it's
So
it's
if-
very hard to sample the permutation.
So yeah, we're not worried about that right now.
Okay. Okay.
We have infinite randomness. The verifier can sample as much randomness as they want to,
Okay.
so long as it runs a polynomial time. So the cost of randomness we don't care about, so long as it's polynomial.
Okay.
And obviously this is polynomial in n. We're not trying to make it more efficient.
Okay.
What you're getting at is things that are computationally bound. So if we assume some computational bounds on the prover, then yes, we can start to use pseudo-random generators and so on, and we can start to talk about hardness in that case, but that's a different story.
Okay.
For now, to keep things simple, prover, computationally unbound. Verifier, polynomial time, but has as much randomness as they want.
Okay.
So, the question is G prime isomorphic to G1 or G2? And it's going to send back its guess B prime. And once again, what does the verifier do here? It's exactly the same as the previous example.
Equals B prime.
Yeah. So let's actually first talk about efficiency. How much work does the verifier have to do? We just talked about this.
Poly.
Yeah, it's polynomial time. So polynomial time just to sample this, assuming that it has, you know, a randomness generator. This remapping will take a polynomial time, and so verifier runs in polynomial time. Is poly time. The prover says computationally unbound, we don't really care. This check can take exponential time, we don't care. How many messages do we send? So it's not quite AM because the coins are random. Sorry, the coins are private, not random. All right. So let's talk about completeness. What is completeness here? First off, what do we mean by completeness in this case? Start from that definition and tell me what does that mean in terms of GNI.
If these two are non-isomorphic, you will accept.
Yeah.
The probability you will accept.
Yeah, so G1 and G2 are not isomorphic, so that means there is no remapping between G1 and G2. Okay, so what is that probability?
Well,
Yes. Not isomorphic. G2 is 1. It's perfect. Prover, a computationally unbound prover can always figure out which one was sent. And it doesn't matter how random this is, always able to figure it out. Okay, so that's great. Soundness. First off, again, what does soundness mean in this case?
If they are isomorphic, then we want the probability that the set is small.
Yeah. So G1 and G2 are isomorphic. So in this case, what that means is that there is a remapping between the two. The two have a common structure. So what's the likeliness, what's the probability that P can fool V in this case?
Oh.
Yes. Because you can show, the proof is actually harder than it seems, because you actually have to show that for a random remapping, the number of mappings to G1 is the same as the number of mappings to G2. So it's a little bit of graph theory trickery you have to get into there. You have to show that the number of possible remappings is the same either way. And it seems intuitively obvious, but mathematically you have to actually prove that. But at the end of that, it's equally probable G1 or G2. So once you go through that mathematical trickery. So if it's equally probable to be G1 or G2, no matter which one we started from, then this does not help in determining B at all. So B prime is at best a guess, no matter how much, because remember, computationally unbounded. So if this is a pseudo-random generator of any sort, and that pseudo-random generator relies on computational assumptions, the prover can break that. The prover can try every possible random combination of like polynomial randomness bits and run them. So this must be truly random. Equally probable, soundness error is, you could say less than or equal to a half. So yeah, so as I mentioned, this is called private coin. You can design a public coin protocol, and there is a transformation where you can take this and make a public coin. We're not going to cover what that is.
Sorry, just curious.
Yeah.
What is the public coin based on if against this computationally unbounded adversary?
I don't remember the transform. Some of it has to do with making things such that you cannot forge. Sorry?
One collision.
Yeah, well, it's like you reveal the randomness, and then you use between that and hash functions. You make it such that the secrecy is no longer useful. Yeah. To be honest, I don't remember what their transform is. I just remember it exists. It's quite clever, and the proof of it is very tricky. But yeah. Okay. Anyone had any thoughts as to how to make it such that Alice could test a random, or not a random, but an unknown class? So Alice now has this random class, and the question is, let's go Corey Pepsi. I'm sort of thinking about this morning, and I think this is a fairly instructive example. So how could we do this without Bob trying to convince her that, let's say this is a restaurant and Bob's a server, but Bob's a cheap fucker. And Alice is a real Coke fan. She comes from Atlanta. She likes her Coke. So she doesn't want to be fooled by somebody that's just saying, oh, no, really, it's Coke. What could she? How could she catch Bob
Can you just repeatedly send the glasses to Bob?
We could. So, but what would we send? Would we send the unknown glass every time?
So I assume that's the only thing we have.
No, you can, you have an unlimited supply of stuff that you know is actually Coke and Pepsi.
Oh,
So you have things that you know are Coke and Pepsi, and you have this unknown glass.
Is this discussion going to lead to some hybrid drink?
No, not quite, not quite. It's actually fairly similar to this one. I was going to use this as a run-up to this, but then I realized it's actually slightly more complicated than I'd like.
But this one is like zero knowledge proof,
Yeah, they're both.
So in this
They're not quite hitting
case,
zero
just to
knowledge.
be sure, in this scenario, we're assuming that Bob does have the ability to discriminate and he wants to convince Alice of this fact, but Alice wants to see that if, assuming that Bob is honest, can I use this ability to
So
what
we
if I got it?
don't know if Bob is honest.
Okay.
So we can't assume Bob is honest.
right?
But if Bob lies, we want to catch him. How can we do it?
You buy a real Coke and
Yeah.
and then you can even can even let Bob see or not, but the thing is that you should flip the two bottom and give it to Bob and ask Bob whether you flip or not.
Yes, you're on the right track. So we're gonna have two glasses. So here we're gonna have glass 0, and here we're gonna have glass 1. And we're gonna flip 2 coins. This is, I think, pretty much what you had in mind. So we're gonna have like bit 0, and we're also gonna have a bit, so bit 0, bit 1. Okay. If B0 is 0, then we put the unknown glass in the 0, the first slot, the 0 slot. If B0 is 1, we put the unknown glass into the second slot. And if B1 is 0, then whatever the other glass is, we give it Coke. If B1 is 1, we get our specified glass Pepsi. So what we say here, we're going to say glass B0 gets the unknown soda, and glass 1 minus B0 gets, if 1 equals 0, Coke, else Pepsi. Yeah, we're gonna have to call this the same, but okay, so B0 prime, B1 prime. And basically, if B prime, this gets a little bit complicated to express. It's easier in words. It's equal to, this is 1 minus B0. B sub B0 equals 1. There we go. So here's the idea. We compare the glasses to what we put in. If the one that we know the one that we filled with Coke or Pepsi, so this one here, matches what we did. So Bob correctly guessed what we asked him to guess. Then we accept his guess for the unknown one, and we use it. If not, we reject. In all other cases, we reject. And so this takes a little bit to reason about, but the idea is we're flipping 2 coins. And if Bob correctly guesses a glass that we fill randomly, then we'll take his guess for the other glass and use it. Why do we have to flip 2 coins? Because if Bob knows that the first glass is always our random guess, or not, sorry, it's our unknown, and our second one is what we're challenging him with, then he's always, let's say he wants to convince us of Coke, he's always going to answer Coke for the first one, and then randomly guess the second one. And even if he can't tell apart Coke from Pepsi, he's just going to, or maybe he can tell apart Coke from Pepsi, and he's going to, the second one, he's going to say, you know, yes, this is, you know, what you expect it to be. And this first one's always Coke. And he can fool us. If he doesn't know which one's which, he's not able to do that. So I leave it as a homework exercise, formalize this a little bit. I mean, all the language is here. And try to reason about what is the completeness and soundness. Again, I only thought of this morning. But this is very similar to this idea, just applied to Pepsi and Coke, where we had to do some random relabeling, right? But we can't do a random relabeling with Coke and Pepsi, so we just add a second glass. And yeah, I'd be very curious if somebody actually comes up with the probabilities here, because I haven't actually worked them out. I'm pretty confident it works. I don't know exactly what problem it is, because I haven't looked it up. But that's fun. I'm just reasoning about this stuff. Cool. Before we go, any thoughts, any guesses as to how powerful is IP? So if you could do any interactive protocol, any number of messages, so long as the verifier is polynomially time bounded, which obviously puts a polynomial time or polynomial bound number of messages, and the prover is completely unbound, how far can we go with this? So, can we do any?
Sure.
Yeah, we can do any. We just, well, actually, we've seen even more than that. Can we do co-NP? Graph non-isomorphism, so far as I know, is co-NP complete. So yes, we do all of co-NP. Can we do more than co-NP? I'm going to give you the punchline, and this is a very famous piece of work. And honestly, I think I've referred to it before. One of my favorite papers of the modern era. IP is the same as polynomial space. So interactive protocols are enormously powerful. Any problem that can be solved in polynomial space, which is enormous. You can do exponential time in polynomial space. It's huge. And the reason being something called sum check. And I'm just throwing this out there so you know what it is. We're not going to have time, obviously, to go through it, but this seemingly innocuous protocol, like this weird problem, allows us to solve basically everything. And the first time I saw this, I was like, what the heck? Why why would you ever want to do this? If you have some polynomial g with there's a restriction on its degree, but relatively low degree polynomial, and this is what we're trying to prove, is that given this g and some value z, we want to prove that if you take the sum of all of these over all of the parameters being supposed to be 0, 1, it turns out to be z. Huh? Yeah. Turns out you can use this. You can reduce true quantified Boolean formulas. So that's something of the form for any x1 there exists some x2 whatever, and then you get, you know, x2 x whatever, something like this. And sometimes you might put some of these literals before or after, whatever, it doesn't actually matter. You can reduce this to subject. And TQBF is p-space complete, because you can take any Turing machine that runs in polynomial space, and you can demonstrate that it is a TQBF. It's crazy to think about. But this is how powerful interactive protocols are. Forget about NP, co-NP, whatever, polynomial space. That's everything. So yeah, that is an enormous step. Now, that's for pure IP. So no bound on the number of messages, no bound on Merlin, Arthur. The verifier is polynomially time-bounded only, and we have these soundness and completeness bounds. And you can show that that can be done for anything in p-space. Again, Shamir's paper on IP equals p-space is utterly brilliant, and technically, to me, not difficult to read. You have to have a little bit of background in IP and TQBF and stuff like that, but it's well written. So I recommend giving it a shot to read it. It's brilliant and probably one of the most incredible recent TCS findings that we have. So highly recommend it. Questions about IP before we wrap? This is my last tutorial. The next two Prashant's going to be teaching, because I think it's next week. There's a holiday during lunch. I think it's the Easter holiday, something like that. So there will be no lecture next week. So instead, we're going to have Prashant teach during this tutorial slot. He's also going to use the last tutorial slot to do a little bit of extra teaching. So treat it as like bonus value for you all. But this is also the first time we have run this course. And it has been my pleasure to teach you all, and hope that it has been helpful. Importantly, please do the course evaluations, including your honest, brutal feedback. If you liked it, if you didn't like it, please put it in there. What we did well, what we can improve upon. Because either way, the more feedback you get, the better. If you like it, obviously, it's very helpful to us to get feedback on what went well and that things went well, because that gets me to convince the department, please let me teach more and please pay me for it. And if there are things that need to be done better or differently, or modules too hard, or homework was too hard, or something was not the way it needs to be, we find that out, we can improve things for next time, or revamp the modules. So yeah, so thanks again, and best of luck with your projects and the rest of the course.